Hi everyone. As he said, my name is Alex, and today I'll be talking about an emulator of a 6502 processor that I did a while back. And before we start, a little bit about me. I'm a college student back at Barcelona for computer engineering, and I'm also working part-time as an infrastructure developer in InFly. And I've been programming since I was very little, and that's about it. Okay, so the main goals of this project were to start learning about how dynamic recompilation works. And for those who don't know, there are basically two ways to emulate a different system. You can basically interpret every instruction in software. So you read an instruction that you want to emulate, and then you basically have a giant switch case where if the instruction I've just read is this one, then I'll do this action, and if it's this other one, I'll do this other action, and you do this for every instruction. That's interpreted emulation. When you do dynamic recompilation, what you do is read a bunch of instructions that you want to emulate, and then instead of just executing them immediately, you translate them into the native architecture, and then you run that translated code in your machine. And that's a technique that allows emulation to be done faster, and it's mainly used to emulate more complex systems than the 6502, because the 6502 is actually quite simple. But I thought that the 6502 would be like a basic and simple way of writing a dynamic recompiler without having to worry about too many things. So the other reason that I chose the 6502 is because back in the day it was a very popular processor. It was used on the Commodore, it was used on Atari systems, the NES, the SNES, and so writing an emulator for that processor would also allow me to play around writing emulators for those systems. Before we start into the process of how to write the dynamic recompiler, let's talk about a bit of the 6502's basics. The 6502 has is an 8-bit CPU, so almost all the registers are 8 bits. It has 6 registers, and it can address up to 64 kilobytes of memory because it has a 16-bit address bus. But the I/O is memory mapped, so you don't have instructions that are dedicated to read and write to and from I/O. It's done directly as if you were reading and writing memory. The registers of the 6502 are the accumulator, which is the register that's most commonly used to store the results of operations like an addition, a subtraction, and all of that. You have the X and Y registers, which can do some operations as well, but are mainly used for indexing into memory addresses. We have the stack pointer, which is also an 8-bit, register. The stack on the 6502 actually ranges from address hex 100 to hex 1FF. So whenever the stack pointer has a value of 0, it would be addressing in memory the address hex 100, and whenever the stack pointer is 255, it would be addressing hex 1FF. And we also have the program counter, which is the only 16-bit register of the processor, and essentially just contains the address of the next instruction that we'll want to execute. We also have the status register, which is the one that stores the status flags of the processor. And the status flags are basically just the carry flag, which is set whenever an operation, whenever an arithmetic operation has a carry or a borrow. We have the 0 flag, which is set whenever an operation returns a value 0, or if we do a comparison and the two values are equal, the 0 flag will be set. We have the interrupt disable, which disables some of the interrupts of the 6502. There are some interrupts that you cannot disable. The decimal flag enables binary coded decimal mode, which is a quite old method of doing arithmetic on processors. The break flag is a flag that is set when an interrupt is caused by a BRK or break instruction. It's quite specific, so it's usually not used, but it's there. And then we have the overflow and negative flags, which is just when an operation overflows, it sets the overflow flag, and when it returns a negative value, it sets the negative flag. Does anybody here know what LLVM is? Yeah? Okay, so for those who don't know, LLVM is a library that you use its main purpose is to be used as the backend for programming languages. So essentially when you write, let's say for example C, you write the C code and then the compiler would translate that code into LLVM IR, which is the LLVM code, and then LLVM itself would compile that LLVM IR into actual machine code that can be run by a machine. This has the benefit that basically you can just decide that you want to write a new programming language and just use LLVM, and now your programming language now compiles for x86, ARM, it could compile to the Nintendo Switch, whatever. It compiles to basically anything. So I chose LLVM instead of writing a compiler to x86 or whatever architecture, because it's, like I said, I'm just doing a dynamic recompiler for the first time, so I don't want to add myself too much work and actually write an x86 compiler. Also, I have some experience working with LLVM, so it wasn't entirely new for me, and I knew a bit how to set it up. It also comes with a dynamic recompiler itself, so essentially we'll write our dynamically recompiled code into LLVM IR, and then LLVM will be the one to compile it to machine code and manage allocating memory that's executable and all of those operating systems things that we don't want to worry about. And also I chose to use LLVM 13 because if I tried to compile anything else or install it, my computer would just break. So I was stuck with LLVM 13, so LLVM 13 it is. But for what we're doing, it's more than enough. Okay, so this is essentially the main, let's say, algorithm of how the dynamic recompilation for this project works. Essentially, we just start with an address in the program counter of the next instruction that we want to execute. So we read that instruction, we update the program counter, and then we translate that instruction into its equivalent LLVM IR. And if that instruction, for regular instructions, we keep doing this process over and over again, but whenever we reach an instruction that is an unconditional jump, so that whatever the case, we are going to jump to a different part of the program, we stop doing this process, and we tell LLVM that we're done recompiling, and that it should now translate that LLVM IR into machine code. So it does that, and it runs that machine code. And the way that we translate the 6502 assembly into the target machine is essentially just one function that has a bunch of inputs about the CPU's current state and everything. And that function returns the value of the program counter whenever that code block that we just translated finishes execution. So for example, if we have a code block that does a bunch of stuff and then at the end jumps to address, I don't know, 200, that function, the function that we have essentially translated, the function that we have essentially written as a translation of the original program would return that 200 value. And so we take that value that the function returned and set it as the new value of the program counter, and then we repeat the process of reading instructions until we find an unconditional jump, and over again that. So just as a bit of an example, we'll be looking a bit of into how this process works with this simple example that doesn't do anything of much use, but has some interesting cases that I wanted to highlight. So, okay, so we start at the compare instruction. The start is just the label that we use to put names to certain parts of our code, so that doesn't need to be translated. We translate the compare instruction into LLVMIR, which is essentially just 3 LLVMIR instructions. So it's 3 comparisons, one for equality, one for less than, and another for greater than or equal. And since none of those instructions are a jump, we just write these LLVMIR into our, let's say, LLVMIR buffer and continue decoding the next instruction. The next instruction is a branch if not equal, which translates into this LLVMIR. This instruction is a jump, but it's not unconditional. It's conditional on that the previous comparison resulted in a not equal. So instead of stopping here, we'll keep decoding the instructions below. But if that branch is hit, we early return from the function, and we return the address of the instruction that we would execute on that branch hit. So essentially, if we compare the previous value to 12, and the comparison says that the value was not equal to 12, we would be jumping to this store. And this store is assuming that our program is at address 0, which let's assume that for now. That store is at address 3. So whenever our translated code hits that branch, we want it to return 3 because it's the address that the processor would jump to. Yeah, so next we translate the increment instructions, which just adds 1 to the accumulator. We translate the store, which for the time being, we'll just say that 3 is a pointer and we want to write into there. And then we reach the jump instruction, which jumps back to the start, translates into a return it translates into our simulated function returning a 0 because it's the address of the instruction that we jump to. And given that jump is an unconditional jump, we tell LLVM that this is the code that we have written, and then now we want it to compile this to machine code, which would translate into this in x86. As you can see, it's actually quite similar to the 6502 assembly. We have a compare, jump if not equal, then an increment, then a move. So yeah, it's quite similar. But obviously this process, as I've described right now, has some obvious problems. The first one is that we told LLVM that 3 was an actual address that it could read and write from, and that's obviously not true. If we tried that, our computer would throw a segmentation fault because it's not an actual address that it can use. So we need a system to tell the emulator that when we're saying that we read and write from memory, we actually want to do something else. So we'll do that by implementing what in Rust is called trade, but essentially it's just an interface that just defines what reading and writing bytes and words actually means. So if we come back to our example, the store instruction is now translated as a call to that write U8 function that we saw before. And to that write U8 function, we pass the address that we want to write to, the value that we want to write, and then some extra information that is basically the internal state of the interface that we're actually calling. The other big problem with this process, well, first of all, now this compiles to this x86. The part that actually changed was just the green box, which moves the different values into the registers that they need to be, and then calls the write U8 function. The other big problem that we have with this current setup, let's say, is that our emulator is not actually keeping track of the state of the CPU. It just has an initial CPU state, and then when it's done, it doesn't update it, it doesn't do anything. So if we were to run the example code before, nothing would actually change, and we would have just written a fancy infinite loop, which is not what we want to do. So to fix that, we'll pass the CPU state as a pointer to a region of memory that actually has the current CPU state. And whenever we're about to exit our function that simulates 6502 code, we'll write any changes that we did to the CPU state back into memory before exiting. So that way, whenever we run a new code block, we have that CPU state updated, and we don't lose any information, and the program runs correctly. I won't go into the details of rewriting the whole example program into LLVMIR. I'll just go over it a little bit. As you can see, it starts by getting the addresses of the accumulator and the flag and loads them, and then it does operations on them. And whenever we're about to return from the function, like in this else and right below here, we store any registers that we updated into memory, and then we return. So that way, if we were to run this function again, we wouldn't lose the state of the CPU. We would keep the state that it was in before it jumped, and use that state, which is what we actually want. Another interesting thing of this method is that we don't have to update the main memory every time we modify a register. Like, for example, when we hit the branch not equal and we early return the 3 there, the only thing that we're actually storing to memory is the flag register. And we're not writing the accumulator value back into memory. And why is that? Well, that's because whenever we hit the branch not equal, we haven't actually modified the accumulator. So we don't need to write it back to memory. But if we hit this jump start, there's an increment up there that has modified the accumulator, so we need to update that value in main memory. I don't know if I made myself clear. Okay, so this LLVM-IR translates into this x86 code with some, let's say, boilerplate removed. It's not necessary to understand the x86 code. I just put it here just so you could see what it translates to. Okay, so now we essentially have a working 6502 emulator, but we cannot do anything with it right now. It just emulates a CPU. It doesn't have a system to emulate. So as a way to see what the emulator actually, to see it working and seeing it do something cool and that we can be proud of, we'll write a very bad, let's say, NES emulator on top of it, so we can see it move sprites and stuff. So as a quick recap of the NES architecture, the main components are the Rico 2A03, which is essentially a 6502 clone. And then we have the picture processing unit, which is the processor that's in charge of writing, of displaying pixels into the screen. And this is the parts of the NES that we will actually be emulating. We won't be emulating any sound for this project because we want just to see pixels on the screen. Obviously, I have no interest in emulating lockout chips, so that we won't do that. And we'll limit ourselves to the 2 kilobytes of RAM that the NES came by itself. We won't be emulating extra RAM that the cartridge could have or anything like that. We'll just keep it simple and emulate essentially just the 6502 processor and also the PPU. But to write this NES emulator, another big thing that our 6502 emulator is missing is a way to handle interrupts. Now, interrupts are the mechanism by which other components of a system tell the CPU to stop whatever it's doing and just take care of something else that has happened that it needs to do right now. As we've written right now, we have no mechanism to handle CPU interrupts, so we'll have to change that. Now, the way that interrupts work on the NES, they happen once every certain number of CPU cycles. So a quite simple and trivial way to implement this would just be every time we translate an instruction, update a counter, and when of the number of cycles that have passed, and whenever that counter reaches whatever number that it is that it needs to reach, we simulate a CPU interrupt. Now, this method of emulating interrupts it's quite simple because we don't have to optimize a lot, and it's also quite accurate because it's the one that most closely resembles what the CPU actually would be doing. But it also has the drawbacks that it makes optimization harder because now between each instruction we have a bunch of junk that LLVM has to be able to separate from the actual instructions to be able to optimize our code. And it also increments the size of our code essentially by, it doubles it essentially, because now every time we translate an instruction, we had to add a bit of extra thing that updates the counter and all of that. But it's the easiest and most simple method that I could come up at the time. And with all this done, now we have a working NES emulator. So I'll see if this works. Yeah, it works. Hallelujah. It doesn't put it in full screen, but whatever. Okay, so here we have the emulator working. Doesn't resize the window. Yeah, but the other reason that I'm showing this video is because, as you can see, whenever we start the game, oh, it didn't go back on the video, it just moved back on the presentation. That's not what I wanted. Hold on. Ooh. Here we are. We'll move this a bit. Whenever we enter a new game, the program doesn't freeze, but it like goes very stuttery. Now this is a design issue with the way that I've written the emulator. Essentially, the problem that we're having is that every time we enter the game, our program reaches a lot of unseen before code. So whenever we reach a code block or an instruction that we haven't reached before, right now we're just essentially stopping the emulation, translating that code, and then restarting emulation. Now this, if we just hit a random code block that we haven't seen before once in a while, it's not a problem. But whenever we reach a section of the program which has a lot of those unseen instructions before, you can see that it makes the program very slow. So the main solution to this would be, it's actually on the next slide. No, here. The main solution to this would have been to, instead of pausing execution of the program and translating, it would be just to send to a worker thread a message to say, hey, translate these instructions for me, and whenever you're done, tell me. But in the meantime, I'll just be interpreting those instructions and just moving forward. This makes the program more complex, but would solve the issue of having those stutters, because we wouldn't be actually stopping the execution of the program. But we would still keep the benefits of dynamic recompilation, which is faster code execution, because if we were to run those instructions a bunch of times, by the time we have called that instruction by the 1,000th time, we would have the translated code, and we could execute that translated code instead of the interpreted one, which would be faster. The other big issue that I see with the way that I wrote this emulator is the implementation of the interrupt handling, which happens after every instruction. A way of handling interrupts that I discovered later is to just handle the interrupts whenever we're doing what I like to call a side effect, which would be essentially writing to memory, interacting with I/O, or jumping to some other place. Because if you imagine, for example, that you had 2 consecutive increment instructions, and then you write that result of 2 increments into memory, it's highly unlikely that the people that made the original program expected an interrupt to happen between those 2 increments. The interrupt probably happens after the store, or at some other point in the program where we're waiting for it. So we could save some space and memory and execution time by not handling interrupts after the first increment, just handle them before and after the store back into main memory. Those are essentially the biggest things that I could have, knowing now what I know, could have been done better. And that is essentially the presentation. If you have any questions, feel free to ask me right here or in private, whatever you want. And thank you all very much for your attention. Mm-hmm. What happens when you have an interrupt whilst you're handling another interrupt?
Can you nest interruption?
The way in the hardware, it's theoretically possible, but programs are usually written in a way that doesn't happen. In the way that it's written in this emulator, you wouldn't be able to do that. It's because the interrupts are emulated in a way that are not actually interrupts. We just know what the NES interrupts actually did. So whenever we encounter an interrupt, we do what that interrupt did. instead of emulating the actual interrupt itself. Yeah.
So maybe it's a silly question, but why don't you recompile the whole program directly instead of going chunk by chunk and then come to...
Yeah. No, it's not a dumb question. That is actually there are tools that are designed to do that. That's called static recompilation, where you take the whole program and recompile it into the native code. That has some benefits, like for example, you don't have to keep recompiling and optimizing and stuff. But also, to do that, you would need a way to, I don't know how to explain that. Whenever I wanted to do that at the first, but the main thing that I encountered that blocked me from doing it is that whenever you find a jump instruction, that jump instruction, it's not always to a specific address. You can jump to the result of an addition of two numbers that you don't know where they come from. So it can be done because there are programs that do that, but I still don't know how I could translate that into actual native machine code. But it can be done. Also, static recompilation for an it's not, static recompilation is usually done to just have a separate executable for each individual game or program that you're translating. So for an emulator, it's not usually done because whenever you hit play, you would be waiting like maybe a minute before the game starts up. With dynamic recompilation, it just starts. So it can be done, yeah. Can you? I don't. Can you speak up a bit, please? I am not hearing you. Yeah.
I want to sing. Okay, so I'm saying that I code in C sharp. So I was asking, what is the chain or stages of translation from a language like C sharp, which is high level, up to this point? Because I want to believe that this point is like this is assembly language, right? What you just showed us now is it assembly language or some kind of low level language? Yes. Yeah, this code, all of this code. This is assembly language. This one, yes. This.
This would be similar to the way the Java and C# work, where the, oh yeah. This would be similar to the way in which Java and C# work, where they compile the Java or C# code into an intermediate language, and then that intermediate language is the one that it's interpreted. The main difference with this is that once we write our code into this intermediate language, instead of interpreting this, we compile this into native executable. So that would be the main difference. You can interpret also these instructions. LLVM also comes with an interpreter, so you can also interpret this instead of compiling it. But yeah, this is the main difference in the way that it works. Any more questions? No? Okay, so then that would be it.